Imagine a time, over 4.6 billion years ago, when our planet was nothing more than a swirling disk of dust and gas, orbiting a young sun. Picture it, a chaotic dance of particles, colliding and merging, forming clumps that would eventually grow into the Earth we know today. It's a wild image, isn't it? But that's how it all began. The early Earth wasn't the serene blue orb we see from space now. It was a violent and tumultuous place. As these dust particles collided, they formed larger bodies known as planetesimals, which were like the building blocks of planets. These planetesimals, some the size of small cities, began to attract more and more material through gravity, growing larger and larger. Eventually, they collided with one another, merging into protoplanets. Among them was the proto-Earth, a young planet still in the throes of formation. But the story doesn't end there. Earth's final size was achieved through one last colossal collision with a Mars-sized object, often referred to as Theia. This wasn't just any impact. It was a cataclysmic event that released an immense amount of energy, enough to vaporize rock and metal from both the proto-Earth and the impactor. The debris from this collision formed a hot, swirling disk around the Earth, a disk that would eventually cool and coalesce to become our moon. Can you imagine that? A moon born from chaos, a sibling created in the aftermath of destruction. Now, you might wonder how we know all this. The rocks that could tell us about the early Earth have long since been destroyed or transformed by geological process over billions of years. But scientists are clever. They study modern rocks, analyze moon samples, and examine meteorites that have fallen to Earth. Each of these has clues embedded within them, like a cosmic puzzle waiting to be solved. For instance, chondrules, tiny bits of dust and rock that survived from the early solar system, help scientists piece together the timeline of our planet's formation. Through meticulous research, we've learned that the process of turning dust into a protoplanet like Earth took tens of millions of years. But the final stages, including that moon-forming impact, may have stretched on for 100 million years or more. It's fascinating to think that the Earth's history is written in the rocks beneath our feet and in the samples brought back from the moon. So, what did the early Earth look like? After that moon-forming impact, it was a dramatically different place. Instead of oceans, it was covered in a magma ocean, molten rock that stretched for hundreds of miles deep, heated by the energy released during the collision. Water? It would have been vapor, swirling in a thick atmosphere, far from the lush blue planet we know. And the sun? It was a fiery ball, emitting intense radiation that could evaporate entire atmospheres. Over time, as the magma ocean cooled, the Earth began to solidify. Volcanic eruptions released gases and water, gradually replenishing the atmosphere and setting the stage for the first hints of life. This was also the dawn of plate tectonics, a process that would shape the Earth's surface for billions of years to come. Imagine massive plates of crust slowly moving, colliding, and recycling materials. This dynamic system is essential for life as we know it, helping to regulate temperatures and create diverse habitats. Now, let's talk about the moon. Contrary to the barren, cratered landscape we see today, the early moon was once geologically active. It too started with a molten surface, but unlike Earth, it didn't develop tectonic plates. Instead, it formed a thick crust of a light-colored mineral called feldspar. As the surface cooled, volcanic activity continued, creating dark basalt plains known as maria. These features tell a story of a moon that was once alive with geological processes, a stark contrast to the desolate image we often conjure. And yet, despite our understanding, many questions remain. Scientists still debate the specifics of that moon-forming impact. How big was Theia? How fast was it traveling? What was its composition? Some even suggest that multiple impacts could have contributed to the moon's formation. New experiments in laboratories simulate these extreme conditions, while computer models allow scientists to explore countless scenarios of impact dynamics. The future holds promise, too. As we gather more lunar samples, we could uncover new insights that challenge our current understanding. Each rock, each mineral, is like a page in the history of our solar system, waiting to be read. With improved measurement techniques, we may discover new chemical signatures that could illuminate the early relationship between Earth and its moon, and perhaps even reveal how moons form around other planets throughout the cosmos. So, the next time you look up at the moon, remember its tumultuous birth and the chaotic dance of particles that led to the formation of our home. It's a story of destruction and creation, of collisions that shaped not just the Earth and moon, but the very fabric of our solar system. The universe is a vast, interconnected web of stories, and we are just beginning to understand our place within it. Isn't that a thought worth pondering?